Hello, this video is to help you with problem number 19 in chapter 4. It's another one of those little Atwood machines I'm sure you guys are learning to love. Um, all seriousness, you definitely need to learn how to use Atwood machines or identify the forces for Atwood machines. It's very popular, um, partially because it's the whole system for pulleys. So anytime you use a pulley system, you're dealing with an Atwood machine. So it's important to understand. For this problem, we actually don't need to know about the free body diagram for this mass on the right. We just need to know the one on the left. I think it's a box, if I remember correctly in the diagram. So I'm going to have the force of gravity. I'm going to call the one on the left mass 1. So I'm going to say this is the force of gravity for mass 1. So just do FG1. And then we know that it's resting on a table. So I'm going to have a normal force going up. I'm going to have Fn. But then there's also that rope. So I'm going to have Ft. Okay. Now, I'm labeling it as the force of tension because it's a rope pulling on the mass. However, that force comes from the weight of the other object, the force of gravity acting on the other object. So I'm just going to go ahead and write that Ft here equals Fg2. Okay. You wouldn't label it as Fg2. You have to label it as a force of tension because it's a tension acting on it, and then the force of gravity for the other mass equals this force of tension. Now, they're giving you three scenarios where Fg2 equals three different values. They don't even give you the mass, they just give you the weight right away. So this is actually a nice scenario. We're going to have Fg2 will be 30 newtons for the first problem, and then for the second problem you have Fg2 equals 60 newtons, and for C they have Fg2 equals 90 newtons. Okay, so to do this, I'm just going to identify the forces we're dealing with. We have the sum of the forces equals the normal force plus, and you would still label the force of tension here sorry, force of tension here, and then you subtract the force of gravity from mass 1, and all of those should equal 0 because they're not accelerating. They tell you that the box is resting on the table, so you know you're not dealing with an acceleration here. And let's see, normal force. Yeah, so we can go ahead and calculate the normal force in this case. And we'll be able to say that the normal force will always equal Fg1 minus Fg2. So now I'm switching Ft to Fg2 because I'm substituting it in. So this and this are the same thing. I said that over here. Did they give us? Oh, and I forgot to write down that they told us Fg1 equals 77 newtons. Okay, so we don't have to deal with Newton's second law at all because they gave us the forces. We just have to use the sum of the forces. So we can go ahead and say normal force equals Fg1 minus Fg2 for part A. So I'm making it line up for A. And then we'll just say Fn equals 77 newtons minus 30 newtons. So we have positive 47 newtons for part A. And you're going to have the exact same equation for part B. 77 newtons will stay, but this time we subtract 60 newtons. So you get positive 17 newtons. Sorry, thought I had to sneeze there for a minute. Fn for the last one, same equation again, but this time we're subtracting 90 newtons. Now that should right away raise an alarm, like, wait a minute, that other mass to the right is more, well, you'd say more massive, but it has more weight to the right. We say weight this time because I actually gave it to you in newtons. So you would say uh, the, the object to the right is heavier than the object on the table. So we know then that it's going to accelerate to the right, or I'm not saying not to the right, but it's going to accelerate. The right one's going to go down and the left one's going to go up. If it does that, then we know that it won't be on the table. Okay, the fact that you get a negative 13 newtons here for the answer, that looks like a 7, tells you that there is no normal force acting on the object. If you remember, a normal force can be only perpendicular out from the surface. We said that, oh, I didn't say it. We should have said up was positive. I assumed it with all the values I put in, but I didn't label it. But if we say up is positive and the surface is obviously below the object, then it's impossible for that surface to put a normal force within itself. It has to be outside of itself. So that negative 13 is not possible. So when you write the negative 13, you then have to explain that the negative value is not possible, and it shows that the box is no longer on the table. So you would write negative 13 newtons. Fit it here. Just say no normal force. But you guys should write it with a complete sentence, like I said earlier, that a negative normal force with our coordinate system would be impossible, and it means that the box is no longer on the table. Okay? Straightforward problem, just need part C. It definitely needs a conceptual explanation.